Good morning. I'll begin by thanking the organizers for giving me this opportunity. Today I'll talk about universality in coupled Burger systems with degenerate flux Jacobian. And this is based on a joint work with Abhishek, Kostia, Manus, and Herbert. And this has been recently published. So I begin by recalling a few facts about 1D Kardar-Parisi-Zhang equation. So Kardar-Parisi-Zhang introduced a stochastic equation to model growth phenomena in 1986, and this is the equation. Here H is growing height field, and B lambda D are parameters, and zeta is zero mean Gaussian white noise. And this equation can be again rewritten by taking a derivative. And after taking a derivative, we get stochastic Burger's equation in slope variable, which is shown in equation 2. So connections to these equations have been observed in many systems, and these systems are often referred to as 1D KPZ universality class. And there are two interesting results in this, very interesting results in this universality class. So one says that the space-time correlation of phi scales with exponent 2 by 3. And this scaling function is a universal function, which is exactly known from the work of Prahopper and Spohn. And another result says that the height fluctuations are of the order t to the power 1/3. And when it is appropriately rescaled, the distributions are well known and depend on the initial conditions. For example, for a stationary initial condition, it is distributed according to Bike-Rins distribution. Now, around the same time, Ertas and Kardar introduced two-component KPZ type stochastic equations, which are shown in equation 5. And their motivation was to model motion of vortex line in presence of impurities. And more recently, Nardis, Gopalakrishnan, and Vasur studied coupled Burger's equations in connection with superdiffusion in spin chains. And these equations correspond to Ertas and Kardar's models with some special choice of parameters. So we revisit this problem, and we rewrite these equations in this form. Here G is coupling parameters, but we will not consider general parameters. We'll focus on this specialization. So when we write the equations explicitly, we find that for phi 1, there is phi 1 into phi 2 term. And in the equation for phi 2, there is phi 1 square and phi 2 square term. But their coefficient is different. So here, when lambda is 1, then these equations decouple into two KPZ equations by taking simple linear combinations. But when lambda is equal to 0, there is no such decoupling. So we do numerical simulations using a scheme studied by Sasamoto and Spohn. And for this scheme, the stationary measure is known. And using this knowledge, we take phi 1 and phi 2 in our numerical simulations by choosing them from standard Gaussian distributions. And we consider periodic boundary conditions. So we do numerical simulations and compute the space-time correlation. And we find that the 2 by 3 exponent is there in these correlations. However, it is quite surprising that the scaling function is not the exact KPZ scaling function. Now we also consider another model, which is shown here. So here we consider a two-lane lattice gas model. It has two lanes. In lane 1, particles hop towards right. In lane 2, particles hop towards left. And for lane 1, all the possible interactions are shown. So these blue particles hop with red 1 if the configurations are like this, but they hop with red gamma if the configuration is like this. So this two-lane lattice gas model was studied by Popkov and Schutz. And their goal was different. But here we we'll focus on density is half in both the lengths, and we'll focus on this parameter gamma is equal to 1/4. Now, for this, we first compute the space-time correlator, and we find that in lane 1, the correlation is very close to KPZ, but I mean, there is still some differences in the tails. And we see that between the lengths, there is cross correlation. Now, interestingly, in this model, if we follow the strategy in nonlinear fluctuating hydrodynamics, where we write down the Euler equations for the conserved quantities, which are densities, and then we expand the currents at these densities up to second order, and rotate these fluctuations and rescale them, we find that the flux Jacobian is 0. So this means that there are no linear terms in these currents. And when gamma is 1/4, the nonlinear couplings are similar to the coupled Burger's equations corresponding to the case lambda is equal to 0, which we discussed earlier. So this suggests universal behavior. So to check this, we transform the correlations according to this rotation and rescaling, and then we compared with the space-time correlators that we got for the coupled Burger's equations. And we find that there is a nice agreement. So this is quite nice. So this, with this, I would like to sum up. So we studied two coupled stochastic Burger systems with degenerate flux Jacobian. We observed scaling exponent of 2/3, but the scaling functions for the coupled Burger's equations is clearly distinct from the exact KPZ scaling function. We unraveled interesting connections between these two models and established universal behavior at certain points in the parameter spaces. And our work has potential implications on isotropic quantum spin chains and one-dimensional beta log gases. And in future, we plan to study the full parameter space of Etas and Kardashev model in more details. So, thank you.
Yeah, we can have a couple of questions.
There's a model very similar to Ertash Kardar, which Rangun Lahiri, Mustansir Barma, and I studied. If you take those two variables, the things that you transformed into phi1 and phi2, if you work in a situation where the average of phi1 and average of phi2 are non-zero, then you have linear waves traveling around. So what you get when you do this transformation when you decouple them into two KPZs, is each one is a KPZ with a wave in one direction, in two opposite directions. So the dispersion becomes wave-like, and you get these things. Do you know what happens in situations where phi1 and phi2 are non-zero mean, or has your analysis automatically covered that case also?
So I think it covers that case.
I see.
But I mean, I'm not sure about your models, so maybe I have to look at it.
Okay, so we can talk to you.
So you mentioned that the deviations from the Rahofer-Spohn scaling is surprising. So could you elaborate on that?
Sorry?
You mentioned, so in your results, that scaling functions deviates from the Rahofer-Spohn one, and you mentioned it as surprising result. Could you elaborate on that? Why is it expected and why it is surprising?
Yeah, so generally, I mean, it is, observed that whenever the scaling exponent is 2/3, the scaling function is KPZ.
But it's a coupled equations now, so why things could have been different?
Yeah, I mean, but it's generally believed whenever the exponent is 2/3, we expect KPZ scaling function, but here we see different things.
Let's thank Dipankar once again.